Hello, today we're going to look at Chapter 10, Precipitation and Agglutination Reactions. I just want to mention that the material in this chapter is quite dense. In fact, the last chapter, the last version of this textbook actually had these broken out into two different chapters. So we are going to try and keep moving this along. I will do my best to remain pithy in my comments, and let's get going. The chapter overview today, we're going to look at antigen-antibody binding, some specific characteristics of those antigen-antibody bonds. We're going to look at some of the assays that we're going to do that are based on a couple of different types of reactions. Some are called precipitation reactions and some are called agglutination reactions. I actually scratched out the instrumentation piece. We are looking at just a little bit of instrumentation, but we're not going to actually do a separate we're not going to follow along with the textbook around the one little discussion about instrumentation, because we're going to do a lot more of that as the semester wears on, and then quality control and quality assurance. So, in general, immunoassays have been developed to identify these antigen-antibody bindings that take place in serum. Of course, it can take place in plasma as well, but for the sake of our discussions, we're going to generally use the word serum. As I said, many of them are based on the principles of precipitation and agglutination, which is what we're looking at today. So it's important that before we get started, we look at some of the key terms that we really need to define before we move further into the chapter. I want to make sure we're all kind of talking the same language. So precipitation, if we look at this definition, precipitation reactions involve combining soluble antigen with soluble antibody in order to, once they bind together, they create an insoluble, ultimately visible complex. So you start out with two invisible things, two soluble things, and when they bind together, they create visible complexes that we can actually measure in the laboratory. Agglutination, on the other hand, starts with an insoluble antigen. Think like a red blood cell or a bacteria, that when it binds to an antibody, which is soluble, of course, they aggregate out to form much larger complexes that are visible for us to see. As a point of reference, we're going to think of precipitation as being kind of a turbid solution, kind of cloudy when we see it, and that's the visible complexes that we see. Agglutination, on the other hand, think about when we do red blood cell typing, and you've got those clumps of red blood cells together. The antibody-antigen binding is such that those large particulate antigens kind of bind together and they get clumpy and they fall out of solution. So that's the difference between precipitation and agglutination. We're going to look at those in much more detail in a few minutes. And then I also just want to bring up the point of multivalency, whether it's multivalent antigens or antibodies. And so a multivalent antigen is defined as an antigen molecule with more than one identical epitope per molecule. That means that has a valency of more than one. And that means that it can combine, as a result, because we have multivalent antigens, we're able to combine with more than one binding site on an antibody. May not be the same antibody, maybe multiple antibodies, but being able to bind to that one larger molecule. So if we have multivalent antigens, more than one identical epitope per molecule. Remember, those epitopes are identical and they're repeating epitopes. And that's when we're going to term them multivalent or even polyvalent. It means the same thing, but I think almost everyone uses the term multivalent. As we remember, not everything is multivalent. We gave an example in one of the very first lectures that we had when we talked about haptens and how they may have a valency of 1. They can be very low valency. But multivalent antigens, we want to have multiple copies of the same epitope on the antigen. Multivalent antibodies then really is referring to how many binding sites the antibody has. Every antibody is multivalent, right? Just by nature of the fact of how the antibody is designed. We know that antibodies have a minimum valency of 2. What has a valency of 2? IgA, the single version, IgG, IgE, IgD, right? Those are bivalent. And the multivalent, so secretory IgA, that means it had the 2 identical IgA molecules bound by that J chain. That has a valency of 4 because it was two antibodies bound by a J chain. 2 and 2 is 4. And then, kind of the granddaddy of valency of antibodies is IgM, because that's a pentamer. So it's 5 IgM antibodies bound together by joining chains, so same kinds of J chains, joining chains. And so we have 5 times 2 is 10. So that is a very high valency, or a valency of 10. So we're going to start out looking at the basics of agglutination and precipitation reactions. And we're going to start with the most important thing, antigen-antibody binding. The principle of the agglutination and precipitation reactions are based on really the binding of this FAB region, the antigen binding region, to its matching specific epitope on an antigen, right? Remember the pathogen, just so we remember, all of the antigen determinants on a pathogen, we know are not the same. In fact, if they were all the same, it would not be a good thing, right? We need to have, that's how we can develop a strong immune response to pathogens, is by being able to, having genetic capacity to be able to identify multiple epitopes. But so these reactions really are looking at how well this antibody binds to this antigen. And that bonding characteristic requires a couple of features or a couple of characteristics of the antibody that we're going to look at in great detail today. And these features or characteristics of the antigen binding reaction are called avidity and affinity. Affinity and avidity, I should say. And we're going to remember, because we're going to talk about it in just a few minutes, that affinity and avidity are governed by what's called the law of mass action. So we're going to talk about these in just a few minutes. We're going to first look at affinity, because that's the first reaction, the first interaction between antigen and antibody. So affinity is defined as the initial attraction force between a single FAB site on an antibody molecule and a single epitope or determinant on the antigen. Very simply put, one FAB binds to an antigenic determinant, and that binding, that initial attraction that brings them together, is called affinity. The strength of that affinity is going to depend on how specific and how well designed this FAB region is for that particular epitope. We're going to see examples where you can have some, we've seen it, you can have a pretty poor antigen, I apologize, you can have a pretty poor antibody developed to an antigen when it first encounters it. In fact, IgM, because it's that initial kind of much less specific antibody, and it hasn't had time to develop really good lock and key fit, actually has kind of a weak affinity. IgG, because that's developed over time in memory, it has a really great affinity. So very high affinity with IgG because it's developed a really effective FAB region specific for that epitope of that antigen, right? We know that about that. When we're looking at avidity in a few minutes, we're going to look at avidity as being defined as really a measurement of the overall strength of the antigen-antibody complex that gets formed. And it's because it's the the strength of all the forces that keep antigens and antibodies together is defined as avidity. So it's not just that single antigen antibody reaction, that initial one that we saw in affinity. It's really taking all of the multiple bonds that are going to form as we form these complexes, and that's going to be avidity. We're going to see in a few minutes, because of its valency, for example, IgM has 10 binding sites, right? Versus IgG's 2 binding sites. So who do you think has the strength of multiple antigen-antibody bonds? Why, yes, it's IgM. IgM has great avidity. Really poor, not poor, but low affinity and but great avidity. And that's because of those really great multiple multivalency that it has. So let's go back and look at affinity in a little bit more detail. So I said that it was the initial attraction force between an Fab site on an antibody and the epitope on an antigen. What does that mean? As antibodies come close in proximity to an epitope, there are all kinds of bonds that can form to hold them together, that initial attraction, that initial bonding. And some of the bonds that can hold an antigen-antibody together include ionic, hydrogen, hydrophobic, or van der Waals forces. So if we go back to remember from chemistry, we'll remember really basically that ionic bonds are held together really by oppositely charged particles, positive and negative, right? Hydrogen bonds similarly refer to, are dealing with positive and negative charges, but it's really talking about the polarity of the attraction of the polarity or the positive and negative charges that live on the hydrogen molecule. It's that polarity, that positive negative charge that holds, that's one of the forces that hold antigens and antibodies together. Hydrophobic bonds are not polar bonds. They're not based on polarity that hold together, but really it's not really as much of a bond as it's the fact that two things that react together, like the antigen and antibody, would rather react together than with the water around it. So they're more the fact that these are both hydrophobic make them stick together rather than bonding to the water that surrounds it. Kind of like, better to be bound to one thing, rather than be bound to the thing you don't want to be bound to. So water's worse, so it stays away from the water and binds to each other. So that's one of the forces that holds antigen antibodies in that initial binding. And remember, we're looking at the bonds that factor into affinity, that initial attractive force. And then finally, the last force that really kind of attracts antigens and antibodies together in that initial binding are the van der Waals forces. And van der Waals, again, are not so much bonds as more of a sort of an attraction between neutral molecules that are, the neutrality is kind of in the cloud around the molecules almost. And so they're more a force of attraction than really a bond. So we have a couple of true bonds, ionic and hydrogen, and we have sort of forces with hydrophobic and van der Waals forces. But together, these really influence this antigen-antibody binding together. And that initial force the initial forces that will bind an Fab site on an antibody to an epitope is called what? Affinity. That's the affinity. They like each other. Yes, they like each other. They really like each other, and they want to bond together. What else do we know about affinity and binding? It's really important for us to remember that antigen-antibody binding is reversible. We're going to see why in just a few minutes. But this is not a done deal. Just because an antigen and an antibody found each other and bound up in this initial attraction doesn't mean that's going to stay that way. Ultimately, the strength of the attraction between the two is going to depend on how specific the antibody is for the antigen. So it's safe for us to say that alone, these bonds are pretty weak. Can cause they're forces that and bonds that can, have that initial attraction take place between antigen and antibody. And once we get that initial bonding in place, it's really how well the antibody, how specific it is to the epitope that's going to determine if the bonding is maximized and remains stable, or if the bonds reverse and the antigen antibody bond dissociates. D-I-S-S, let me spell it, D-I-S-S-O-C-I-A-T-E-S, dissociates, because it's not that specific. So you don't have to have a great specific antibody to have that initial reaction take place. You just have to have some of these forces that drive them together. When we look at this slide, we can see in this illustration that's trying to demonstrate affinity that the same antibody, presume these two antibodies are the same, it's just two different arms of the same one, combine multiple epitopes or determinants, right? So we can see these are not identical antigens, right? But they're both bound to the same antibody, right? The two antigens resemble each other enough so that there's that cross-reactivity that we've talked about so many times between the antibody, not only with its true target, imagine this is its true target, but it also combined with something that's kind of similar in structure. But if we look closely at this illustration, and this is on page 141 of your book, we can see that the binding on the left is stronger. Number one, this has a better fit. It's more, things are more lined up. The positive lines up with the negative. Here it lines up, whereas these are not really binding up the way you would expect. So not only is it a little bit better fit, but that charge distribution between the antigen and the antibody is better in this one, in its true specific antigen for that FAB. So even though there was this initial attraction, this initial binding, this one with a higher affinity, a more specific binding, and better, a stronger binding, it has a higher affinity, and that's going to be the one that sticks. That's going to be the one that initial attraction is going to be higher. It's said to have a higher affinity. It has a higher strength to it. So it's more likely that this reaction will hold than this one with a lower affinity. And doesn't that make sense? Higher affinity means it's more likely that the antibody antigen bonding is going to take place because it's really just a better match. It's a better match. It's a more specific match. This antibody is matched to this specific antigen. The binding took place, wasn't a great one though. And so this has a lower affinity and is less likely that the bond will remain together, may dissociate. It may be overcome by other things that we can see in a few minutes, but it's got a lower affinity, and left to itself, it's not going to necessarily stay holding the bond. So which one has the higher initial attraction? The one that's a better fit. This is just another picture that we talked about. So we just talked about really when we're talking about affinity, the strength, how the strength of the antigen-antibody reaction is dependent on the fit of the elements or the specificity of the elements, right? So if we use the lock and key analogy we've spoken about multiple times this semester, affinity, or the strength of the initial bond between the antigen and antibody, is dependent on the fit to keep it a longer, stronger bond over the long term. So if we look at the picture here, The one on the left also has a higher affinity, and this is what this was trying to reflect here, that it was a better lock and key fit. If we imagine these are the poles here, the electrical charges, the polarity, whatever it is that's holding these bonds in place, electrical charges. This is a better fit clearly than this, right? And so even though these maybe were held in place, there was some initial attraction that allowed it to fit in there. This was not a great fit, so the bond is not as strong. So high affinity versus low affinity. Just as a reminder, the better the fit, the stronger that initial affinity or that initial bond will be. The weaker the lock and key fit, like with a cross-reactive antigen, the weaker that the bond is going to be. And this kind of a bond that isn't a great fit is much more likely to what? Oh, good, there I did. Dissociate. It's much more likely to break apart. And that's because it's not a great fit. High affinity is a great fit, great bonding, strong bond, tends not to dissociate. Low affinity tends to dissociate because it's a poor fit. They both bound because of that initial affinity, that initial attraction, but it's the strength of that bond and how well of a fit it is, how specific this antibody is for this antigen, that determines whether the bond sticks. Does this make sense? I sure hope so. Let's turn to avidity. And avidity is, we're no longer looking really at that initial antigen-antibody binding. What we're looking at is really the combined strength of all of the forces that keep the antigen-antibody molecules together. So it's the sum of all the forces between an antigen and an antibody that keep that molecule together. And so when we talk about the thing that really impacts avidity is the strength of being able to have multiple antigen-antibody bonds holding the molecules together. And we talked about the valency of each of the different kinds of molecules, the immunoglobulins, and why the valencies are important. We're going to see in just one slide how valency is going to play a huge part in that. As I said, that once you get that initial bond, it's easily broken. But if we can have multiple bindings at the same time, it's much harder to rip it apart and to dissociate. So when we spoke about IgM having a poor affinity or a weaker affinity because it wasn't developing really specific FAB regions to an epitope, right? It hasn't developed that perfect lock and key fit with an IgM. But guess what it has? It has the ability to bind a lot of those epitopes. And it's sort of, I joke, it's kind of like brute force holds it together. So a high valency can overcome a weaker initial bond. Let's take a look at the next slide and you'll see what I mean. So if we look at this picture, here's a great example. So this is a bivalent immunoglobulin. Let's pretend it's an IgG, right? And it binds to one antigen determinant site, one antigen determinant on an epitope or on an antigen, right? Imagine you're, swinging off a roller coaster at, 10 stories up, and you can hold on with one thing holding you in place, and otherwise you're swinging in the wind, right? The likelihood of that dissociating or breaking apart is stronger than, let's say, you're able to hold on with two, right? You're able to hold on with two means of support to hold you to something that's floating in, 10 stories up. Now imagine that each one of the binding sites of this IgM binds to an epitope. Now remember, this is a two-dimensional picture. Remember how we have the hinges and they can bend and twist? So that these molecules can actually bend and twist up and over, and they can hit antigen binding sites on it. We don't have to look at this in a 2D model. This is just the representation. But now, even on this picture alone, we have six antigen FAB, I apologize, 6 epitopes bound to 6 FAB regions out of 10. So just by, sheer force of numbers of bonding sites, this ends up with a very strong bond. And so what do we know about avidity to sum this up? Avidity becomes less likely to reverse because you're binding more FAB sites to the antigen. The number of bonds that take place influences the overall strength of the binding and thus really the stability of that antigen-antibody complex. So avidity is influenced by the valence of the antibody, and this is why it was important for us to have multivalent antigens, as well as the valence of the antigen. If you only have very few antigenic determinant sites on this, a valency of 1 or a very low valency, there's less likely that some of these non-specific antigen bindings can take place. So high valency or multivalent antigens as well as multivalent antibodies makes a stronger overall bond. This is going to be important to us as we're going through this, because we're going to see in reactions, in some cases, IgG is a really terrific immunoglobulin for us to be using within the test system, and in others it's IgM. But we want to remember that avidity and affinity, or affinity first and avidity second, really both influence the bonding between antibody and antigen in different ways. Oops, I only thought we were done. Okay, so taking everything we've spoken about in consideration, the immunoglobulins with low valency tend to be really very specific to the epitope it binds to. And that's what it uses to stay bound. It doesn't use so much the valency, but it uses the specificity. Which antibodies do we know are more specific? Well, those are IgG, right? And those have a lower valency. It has a valency of only 2. High valency, as I said, can compensate for lower affinity. And so if we look at this representation of first exposure to an antigen and second, it makes sense. What we're seeing now in the impact of both affinity and avidity in those bindings makes a little bit more sense. So let's take a look. In this first reaction, when you're first exposed to something antigenic, this was showing it was an immunization, but it could have been a pathogenic exposure to bacteria, to anything, right? We'll just say this is your exposure, your point of exposure. What do we see first? We have that brief lag, right? And then we start to develop what? IgM. And we develop IgM in a larger quantity than we do in IgG. So this, in this slide, this represents the IgM, and this difference is the IgG. This curve right here represents the total IgG and IgM. So we have much less IgG produced in the initial response. What do we know about it? IgG is developed very quickly, and it's not a very good lock and key fit. That's the kind of poor lock and key fit. It matches, but you got to jiggle the key to open the door. IgG that develops later is a much more specific one. So, isn't it good news that IgM has a valency of 10 that's going to overcome this poor kind of specificity? And that in the second immune response, when we produce mostly IgG, which has a valency of 2, it has a really, really specific, really great lock and key. So we don't need all of those binding sites to hold the bond together, because the specificity of the antigen is so good for the antibody. Nope, backwards. The specificity of the antibody that's produced, the IgG that's produced, is so strong and exact to the epitope that we were exposed to. So avidity and affinity can really be seen in this primary and secondary immune response when exposed to a pathogen. take a look at this, spend a little time with it, and I think that as you do, it makes sense, and this will help you to understand avidity and affinity, that initial response, but it's not very specific, versus avidity, which is the valency of binding and how strongly they bind to influence things dissociating or staying together. Both are important in their own ways, and both play an important role in antigen-antibody binding. So one last little kind of quirky thing. We're going to be speaking about the law of mass action. And as I said before, all antigen-antibody binding is irreversible. So if we look at the reaction here, this can be illustrated by looking at the free reactants being in the same concentration as, that should be that does not mean a minus. I probably should correct that. That really is talking about antigen complexes. So this means antigen-antibody complex. So the amount of complexed antigen-antibody is roughly equal to the amount of free antigen-antibody. And they're in equilibrium. They're in equilibrium within each other. And when they are, you have some forward reactions and some reversals of the reactions. You have some of these dissociating, you have some of these binding, right? Some binding, some dissociating, and in general, we're keeping those in relatively equal parts within the serum. However, because antigen-antibody binding is governed by this law of mass action, we're reminded that even though free reactants are in equal parts to bound reaction, roughly, that we have to factor in something else. We have to factor in the strength of the binding in determining the likelihood of this reaction dissociating. So it's not just a concentration of reactants, it's the concentration of reactants and the strength of the bonding. That strength of the bonding is really going to be important when we're talking about designing laboratory tests in order to identify the presence or absence of antibody or antigen, and looking at the lab tests that we do. So we use this law of mass action in the calculation. This is the calculation for the law of mass action, where K is a constant, and it represents really the difference in the rate between binding versus dissociation. And so it's going to factor in that rate of whether it's going to bind or dissociate. How strong is the bond that it's either going to bind or dissociate? And it's characterized by the complexes of, and the concentration of the complexes that are bound, the antigen-antibody bound, divided by the free reactants, the antibody times the antigen, right? So this is where we're at. I know this is a little funky, but stick with me. I'm giving you two examples that we're going to look at the calculation of the K, the constant, which represents the difference between either binding or dissociating of this reaction, okay? So if we assume that we have 100 units of bound antigen-antibody complex and only 20 units of free reactants, we end up with a K of 5, a constant of 5. So we're saying that the constant of the difference between, there's 5 times more complexed than free, right? We're still with me. Let's look at the K if we have only 20 units of complexed versus 100 units of free antibody and antigen. We end up with a constant, or the difference in rate of binding versus dissociation, is very low. It's only 0.2. And so if we're imagining that a larger the amount of antigen-antibody complex, we end up with a higher value of K. These are going to be the reactions that are going to, clearly these are the ones that are remaining bound, right? And these are the ones that ultimately are going to make good lab tests for us because they're going to be remaining visible or easily detected. Remember, free reactants, soluble antibody and antigen, are not visible on their own, right? Bound ones, they fall out of solution and they're visible to us. So we want lab tests that end up with a higher value of K, a higher likelihood that we have more antigen-antibody complex. How do we know that it's more likely? Because we just see it. We see it in action. We have equal amounts of reactants, but most of them are remaining bound. Why do they remain bound? Because we have a strong, we have a strong affinity and avidity, mostly avidity, right? So we have that really strong binding. And that's what the law of mass action is telling us, is that really, all things being equal, we should at any given time have normal antigen-antibody binding in equilibrium. And when it is, it's reversible. But once you get to the point that you have more units that are bound together, a stronger binding, it's much harder to make this reversible reaction take place. And those are the lab tests we want. Let's see. Anything else? So tests that we use, we want to have tests that have very high avidity, and we also want them that are going to have, we're going to see that high avidity and even high sensitivity, that specificity of antibody to antigen results in more of these bound complexes forming. And that's going to cause really easily detectable reactions. That's what we're hoping to see. So again, spend a couple minutes with the law of mass action. It's really not, it's really just telling us that we're looking to see that this constant that gets calculated, it's really just telling us how likely it is that we're going to keep the complexes bound versus allowing them to dissociate. And only the tests that we want to do are the ones that are going to keep it bound, because these ones with a low K value are typically going to dissociate and would be a poor lab test for us. So that's the antigen-antibody binding characteristics that are governed by the law of mass action. So I don't know if I told you at the start of this, I did say it in the portal. This is the first question that we're going to have. So this is kind of a poor question. Let's specifically say, which is preferable in laboratory testing? What kinds of avidity and affinity do we prefer? We prefer tests with what? High avidity and high affinity. We want a great initial binding, and we want a great firm binding. So the preferable laboratory tests, answers to question 1, you should get this: high affinity and high avidity. So now we have a sense of antibody-antigen reactions that we're going to be testing in the lab. Let's start to look at some of the lab reactions. There are going to be multiple factors that are going to influence the antibody-antigen reactions in the lab. Some of the things that are going to influence them, well, doesn't this make sense? The concentration of reactants. Is there more antibody than antigen? Is there more antigen than antibody? What's the concentration ratio of antibody to antigen, or vice versa? Temperature, how long we incubate something, pH of a test. Those are going to be important things, and we'll talk about those later. But for right now, we're going to focus on sort of the relative concentration of antibody and antigen in the test. First, we need to spend just a few more minutes before we move on to this, to the tests, talking about how antibodies and antigens react, and the phases of antibody-antigen reactions that lead us to get to see something visible in a laboratory test. So we understand the concepts of FAB regions of antibody binding to an antigen. We understand that, right? We're good. That's the easy part. That first part is called sensitization. That's all that is, sensitization. It's antibody binding to an antigen. We're going to take a look at that in a little more detail in just a second. The second thing we're going to look at is, so that's called the primary phenomenon, or sometimes we call it a phase. Primary phenomenon is called sensitization, and that's just binding antibody to antigen. Bam. The secondary phenomenon is formation of what we call a lattice formation. It's almost like a little lacy formation, and this is going to be a really simplified version that we see in our text, but we're going to see how one antibody can bind two antigens on two epitopes on two different antigens. So this one antibody binds to an epitope on this antigen and an epitope on that antigen. This is where it's really helpful if when we have those reactions that there can be multivalency on the same antigen. If I only had one, if I didn't have those repeating antigens, the antibodies, I would never get to this cross-reacting. I wouldn't get to the point that if I didn't have this, I didn't have this, and I didn't have this, I could bind this antibody to this antigen. But if every other antigen was different than this one, the same antibodies wouldn't react, and we wouldn't get what's called a lattice formation, or basically kind of cross-linking between one antibody and multiple antigens. Imagine now you have IgM with 10 of these binding sites and how much they can form in lattice formation, right? Lattice formation, the secondary phenomenon, is going to be important in visible agglutination. We're going to see that. The tertiary phenomenon we're not going to talk about today because it really talks about the impact of these agglutinants, or these precipitated complexes, and how it affects tissues and cells, usually in a very negative way. So we see an end product of a buildup of these complexes. We're going to talk about those later this semester. There are times when the buildup of immune complexes in the tissues can have a detrimental effect on the host, but we're not going to talk about that today. So, well, let's look at the primary phenomenon, or sensitization, really quickly. Quite simply, the sensitization is the reaction of one antigen binding to one FAB region of the antibody. And it's illustrated here. These happen to be red cells. It could be the epitope of any kind of an antigen, though. So, but it's one antibody binding to one antigen, one FAB region of an antibody binding to one epitope. This theoretically could bind to another one on the same cell. It can, it doesn't necessarily, and some will and some won't, and that's okay. This by itself, though, in the laboratory, so let's say we're looking for antibody in the patient's serum to see if they bind with a known antigen. And we get this binding of one soluble antibody to a cell. Can I tell visually, or even do you think by instrument alone, that this has taken place? No, it's not a visible reaction. It's really important to remember sensitization is not visible, so it's not something that's easily determined in lab testing. We're going to be able to see tests in later weeks where we can do things to manipulate this. Maybe we attach another antibody to this that has something that's going to cause another reaction, a colorimetric or an enzymatic reaction. But this by itself, not visible, and that's what we're talking about today. So the primary phase or phenomenon is called sensitization. It's not visible. It's a single antibody to a single antigen. We just learned that that first phase of an antibody, that affinity, is rapid and reversible, right? It happens very quickly. You put the antibody and the antigen together, bang, they bind, and it tends to be a very reversible one. The antibody affinity and avidity to this binding influences how well it's going to stick. IgM we're going to see is much more efficient in this than IgG because of that valency, right? That avidity, that strength of 10 bonds versus the strength of 1 is going to be much more strong. It's also going to be much more efficient. They say that IgM is 700 times more efficient than IgG in binding. So that's clearly much more efficient. And that, as I said, you have to have enough epitopes on the antigen. And if there isn't, if there's not as many antigen determinants, or maybe they're not easily accessible on the surface of the pathogen, then it's much less likely to interact with the antibody. So there are structural components to antigens that influence this as well. But really just remember, sensitization is one antigen, one antibody, and remember especially that it's not visible and it's reversible. Yes? Great. Lattice formation, though, happens once the once the antibody gets sensitized onto the antigen. The second phase we see is that cross-linking of binding one antibody to another antigen. If you remember back when we were talking about antibodies, I told you how the hinge region of antibodies allows antibodies to bend and twist almost like in a game of Twister. Well, that will come in super handy here. The simple illustrations that we see in the book really don't reflect it, but this is the way it is. This could bend here. There could be a bend at the hinge here, and this FAB could reach all the way up and around over here and bind to an antigen over here, for example, right? So the cross-linking doesn't have to be this nice little, pentamer kind of a thing. 1, 2, 3, 4, 5. Yeah, I was making sure after I said it that there really were five sides. But in fact, it could be, the hinge can make this contort in many different ways. So once we get that the first sensitization, then the antibody's binding starts to repeat, and the second FAB region of an antibody can bind to an epitope on another antigen. And what happens is, the more of this binding that takes place and the more of these complexes that form and the bigger that it forms, the antigen-antibody complex gets bigger and bigger, and it becomes insoluble, and it becomes visible in the form of either precipitation, if it started with both soluble antibody and antigen, or in the form of what we call agglutination, if we started with first with an insoluble structure like a red blood cell plus soluble antibody. So if we remember back to that description on the keywords of precipitation versus agglutination, precipitation is the formation of these complexes when the antigen and antibody were both soluble. Agglutination was the formation of these visible complexes when we had one insoluble structure plus a soluble antibody. So conceptually the same idea, though, of lattice formation. Unlike sensitization, lattice formation is what? It's visible. We can see this in the lab, and that's a good thing. So what else do we know about lattice formation? Lattice formation is they say it's the sum of the interactions between antigens and antibodies. What does that really mean? It's the complex of antigen and antibodies. One antibody to multiple antigens, to the epitopes on multiple antigens. So this is a great example. I'm trying to see if any of these are kind of twisty. None of these are still very good examples of kind of a bending of a hinge, but it's the way it is. There are conditions that we can see, especially in the laboratory, that can influence how well this reaction takes place. And sometimes we have to give it a little bit of help. and sometimes there are things that we can do. So there may be some physiochemical factors that are going to influence how well these bind together and create this lattice that we may have to adjust our testing. Let's see. We're going to talk about these in greater detail when we talk about agglutination, but we're going to remember things like ionic strength, pH, temperature, even electrical charges between red blood cells can be important. I will mention that in laboratory testing, IgM molecules like it to be cooler. The test reaction is best in the cold. IgM are what are called cold antibodies, so they like it cold. 4 to 27 degrees Celsius, I think, 27. Whereas IgG likes it at body temperature. So anywhere between, say, 30 and 37 degrees are really helpful for IgG to have optimal lattice formation and binding. We're going to talk about these electrical charges in just a few minutes. Just remember, there are some physiochemical factors that affect how well this takes place. Let's move ahead now to looking at precipitation reactions in the laboratory. So we saw how the lattice formation resulting from antigen and antibody binding takes place, and how precipitation reactions was when you had a soluble antibody and a soluble antigen producing those insoluble complexes that are then visible in laboratory testing. We're good with that, I think. So the first immuno assays that were done really used this concept of discovering these insoluble complexes that could be formed. We know, because we've talked about it, that antigen and antibody both have to be multivalent, right? They have to be multivalent for the specificity for each other. And what else do we know? We need to have equally relative concentration of both antigen and antibody, or else this reaction is not going to go well. We're going to see in a few minutes what happens when you have an excess of antigen or an excess of antibody in your test system. What else do we need to know? We need to know that precipitation reactions, because it's an antibody-antigen reaction, what are some of the things that affect it? Exactly what we expect: avidity, affinity, and that concentration of antibody-antigen present. We're going to talk about the fact that optimum precipitation occurs in what's called the zone of equivalence, which is really telling us that antibody and antigen are present in relatively equal or equivalent amounts. And let's see, the next slides are going to tell us why. So let's see what happens. This picture, this illustration that we see here, is what's called the precipitation curve. And we're going to look at the zone of equivalence. You can see this area is called the zone of equivalence. And right here, what do we have? We have those insoluble lattice formations forming, which are exactly what we want to have happen. There are two other areas of the curve where antibodies and antigens are out of equivalence. So in the zone of equivalence, multivalent sites of antigen and antibody are approximately equal. So if we have IgM here, we have 10 antigen binding sites. We have 10 antigen binding sites, we have 10 epitopes. So roughly, they're not, you're not counting this exactly, but they're roughly the same. And as I said, precipitation reactions have to be run in that equivalent zone, that zone of equivalence. This picture is in page 142 of your textbook if you want to follow along, if this isn't big enough. When the amount of antibody is in excess, like we see here, we have more antibody. We have 1, 2, 3 antigen and 1, 2, 3, 4, 5, 6, 7 antibodies. So we have 14 antigen binding sites, or FAB regions, and we have 3 antibodies, each with, looks like 2 epitopes. So there's 6 epitopes and 14 FAB sites. So clearly, antibody far exceeds the amount of available antigen. What happens is there's so little antigen, you can, even if this one binds here, there's never enough availability of antigen for us to cross-link this antibody to ever get this to the point that it precipitates out in lattice formation. There's just not enough epitopes for this to form a lattice formation. So you can see that, you know, one other antibody could come here and bind off here, and one could bind off here, and then you're done with your epitopes. You've got no more binding. So you have no way to form that required lattice formation for testing, right? We call this area where there's excess antibody, we call that the prozone. And that's talking about more antibody than antigen. There's a inequivalent amount of antibody to antigen. So if we, however, have an excess amount of antigen to the amount of antibody. So again, if we counted this up, we have 2, 4, 6, 7 immunoglobulins, so at 2 FAB sites each. So we have 14 binding sites, and I have 2, 4, 6, 8, 10, 12, 14, 16, 18, maybe 20 epitopes, 20 antigens with 2 epitopes each. So I have 40, is that right? Yeah, I'm going to just pretend it is. 40 epitopes and only 6, 8, 12 FAB sites. Well, there's clearly more antigenic binding sites than antibody. And the illustration says it very clearly that what happens is that the antigens bind off all of the quickly. Remember sensitization? I said happened quickly. That initial antibody antigen binding happened quickly. Well, what happens? Antigen binds off to those FAB sites very quickly, fills up all of the available FAB sites, and there's never an availability or a possibility of getting cross-linking because there's no open FAB sites to bind to another antibody. We call this lack of a lattice formation due to excess antigen. We call that the post zone. So it's after the zone of equivalence. The prozone and the post zone. And the zone of equivalence is right when you're in that sort of sweet spot where you have basically equivalent amount of antibody and antigen. That way the antibody can bind to more than one antigen, forming a stable lattice that's now visible. That's going to be our ideal testing area. I don't think we have to spend a lot of time here. Let's look quickly. Prozone, antigen combines with only 1 or 2 antibody molecules, no cross-linking. False negatives may occur as a result of the high antibody concentration. Doesn't mean that there wasn't really the right antigen there. It just means we couldn't detect it in the test. So it's a false negative reaction because we never saw that lattice formation. If I should say, if you suspect false negatives due to high antibody, believe it or not, you can make a dilution of that serum, and it's a strange phenomenon. But when you make a dilution of excess antibody, the antibody dilutes out faster than the antigen. It seems like it would be equal parts, but it's not. It has to do with how the reaction can take place. And so a dilution frequently will help this false negative if you think you have excess antibody. It's just one of those little quirks of the lab. The post-zone phenomenon, because antigen is in excess and no lattice forms, sometimes what you can do is wait a week. So if you get a false negative, so you had too much antigen, you had no lattice formation, right? We saw that here. Too much antigen, no lattice formation, right? The small amount of antibody leads to what? True negative or false negative? false negative, because guess what? There really was antigen there, right? So false negative results. Sometimes you can repeat the test like a week later, give the patient time to produce more antibodies in that, they may be at the very first stage, post-lag phase of antibody production. Give them a week and have them come back. And if the test is still negative, it's unlikely that the patient has the antibody to whatever you're testing for. It really is. Sometimes the physician, when they suspect someone has been exposed to someone and they're testing for the antibody in their serum, they just tested a little bit too soon. You got to wait until people have enough time that 7, 8, 9 days to get that first IgM antibody production started. So if you don't wait long enough, then you get a false negative. And you can sometimes have a patient come back a week later. If the test is negative again a week later, it's highly unlikely the patient was exposed. This is just a summary of what we just talked about, just another picture for you to understand and look at. And you can spend some time on that if you like to. These next two slides really are just, I could put them at the end. These are just a nice picture of where we're going in a few minutes, and it's kind of a summary of the reactions that we're going to be looking at, the precipitation reactions that we're going to be looking at in the next few minutes. So let's take a look at precipitation reactions. Again, we're going to be looking at turbidimetric, nephelometric, radial immunodiffusion, which is not in your book, but I thought it was good just to get a snapshot picture of it. We're not going to spend time on it really. Sadly, we are going to spend time on Octolani, which usually gives people a headache, immunoelectrophoresis, and immunofixation electrophoresis. So let's take a look at these. So now we're up to the point that we have seen antibody-antigen reactions. We have seen the characteristics of avidity and affinity. We've seen how the law of mass action and the relative equivalence of antibody-antigen complex to free reactants influences how strong the bond is. We've seen how the zone of equivalence and either the pro-zone or the post-zone affects the lattice formation. Let's imagine we get to the point that we have done it, we have a test system, and we've combined antigen with serum from an antibody. You can really look for either antibody or antigen, but we've developed a test system, whatever it is. We have antibody-antigen complexes forming. Those lattice formations have formed in the test system. In precipitation, remember they started out soluble and soluble, ending up with visible complexes. When they get formed at a relatively high rate, they precipitate out of solution, causing what we call a turbid or a cloudy appearance, right? We know what turbidity looks like. We're all in urinalysis. And cloudy, it's kind of hazy, right? Turbid is kind of hazy. So turbidimetric testing measures the turbidity or cloudiness of a solution by measuring the amount of light that passes directly through the solution, versus nephelometric, which is going to measure, it's an indirect measurement that's going to measure the amount of light that gets scattered. So let's take a look at these two. That's the definitions of them, and let's take a look at them in a little detail so that you can see what I mean. Oops, this is just an example. Oh, this is just a nice picture of a nice clear solution that has clearly no complexes formed that haven't fallen out of solution. So there's no precipitant. This has precipitant at the bottom. That's still even a little cloudy within the solution. So this precipitant means there's immune complexes there. There's nothing here. This is kind of a scratchy tube, but there's nothing here. So this is negative and this is positive, right? This is the precipitant at the bottom is those immune complexes falling out of solution, indicates a positive reaction. As I just said, turbidimetric and nephelometric testing is going to take a look at the cloudiness and measure it. So turbidimetric or turbidon, it's harder for me to say this. turbidimetric. I can't say it. That's why I say honestly, it's why I say turbidimetric, because I know I have a hard time with turbidimetry. Turbidimetry? Honestly, I have a hard time with that word. I avoid it at all costs. Turbidimetric testing measures the cloudiness of the solution caused by the immune complexes falling out by measuring the amount of light that passes through the solution. So imagine you have a cloudy solution and you have a light source over here with a lens, and then you have you're able to measure here the amount of light that passes through. So you pass a light source directly through, you have to invert the solution, make sure it's well mixed, and then you put it in, could be a spectrophotometer, most likely is like a spectrophotometer. Pass a light through it, and you get the measurement of the light that passes through. You have the initial reading here, you know how much light you started with, you measure the amount of light that passes through, and the difference is what didn't pass through, because every time the light hits a particle within here, it gets scattered off. And we don't count that. We count only the stuff gets to this detector unit. So turbidimetric testing tests for the amount of light that passes through a cloudy solution and gets measured on the other end. We are going to use a standard curve in just a minute to calculate how much it is and how much the variance between the original light that was transmitted and the light that was collected at the end, what the difference is. It reflects how cloudy a solution is. The more antigen and antibody binding that there is, we know that there makes more of those immune complexes that are visible. And so less light can pass through. So remember, each one of these dots deflects the light. So if you have a ton of dots, less light passes through. More of it gets deflected off to the side. Does that make sense? I think it does. It's pretty straightforward. If you've ever used a spectrophotometer, then you know what this is. And we'll certainly be using a spectrophotometer in chemistry in the next semester. So that will be something you'll be spending some time with. So we capture the amount with a receiver on the other end, and then we're going to, as I said, use a standard curve. So what do we do? To determine the amount of the substance that is being detected, we're going to compare the sample results that we get, how much light passed through, on a graph called a standard curve. And I don't know if you've done one before. And when you prepare a standard curve, I have a slide in just a moment for this. It's important to remember we prepare what's called a standard curve, and it's prepared from known standards, which are known as calibrators. The difference between a calibrator and quality control is that a calibrator comes to us, and the manufacturer has told us the exact amount of whatever it is that we're measuring. That is, it's exactly 50 milligrams per deciliter. Exactly. Quality control, on the other hand, are substances that are in similar ranges, low, normal, and high, to a patient sample. So that's why we run 3 levels of control. We run a low control, a normal control, and a high control. And these tell us kind of a range of what it is we're testing. We're no longer exactly 50 milligrams per deciliter. When we run this, it's someplace between 43 and 56 milligrams per deciliter, and as long as you get that result, it's good enough. So this is a standard curve. We're going to use calibrators to do it, and then we're going to check the validity of our standard curve using quality control. Just as a reminder, turbidimetric testing is very simple, but not very sensitive. Why do you think that is? I think it's because a lot of things are, I don't just think, I know, honestly, a lot of things are glutenate, right? A lot of things, you can have non-specific antigen binding to antibody, right? So you're not necessarily getting binding only of what you want. So simple, it gives you a good screen, but it's not a perfect test. Let's look at preparing a standard curve. I have down here a video that's going to go a little bit slower for you. It's not a perfect video. It's not bad. But and I'm hoping you've done it before. And if you haven't, we can talk about this on either Thursday or the following Thursday when we meet. And I'm happy to do an example of a standard curve with you on the board. Someone just needs to remind me. So, as I said, when preparing a standard curve, we're using calibrators of a known value. Remember that 50 milligrams per deciliter. Some manufacturers sell you a calibration kit with anywhere between 3 and 5 calibrators. But if you have, some of them sell you one calibrator and you make dilutions yourself. You make serial dilutions, for example. And you need to always have at least 3 points on a calibration curve. Why is that? If our calibration curve, if we only use 2, here's 1, here's 2, and then you draw the line between the 2 points, it's a slight difference, but it's not the same. So what we do is we run at least 3 and we draw the best line between the 3. So we have, the best 3 is not always 3 exactly in a row. Sometimes it's 1 a little low and 1 a little high and 1 directly through. So you always need at least 3 points for a calibration curve. This one happened to use 5. And then you perform testing on it using, say, a spectrophotometer or an automated analyzer. So let's say we had our original calibrator that was purchased from the manufacturer was 5 millimoles. We diluted it. Let's pretend we did a dilution, which doesn't even make sense because these aren't a dilution. Let's pretend we bought a test kit that had 3 dilutions exactly the way it is. When I prepared this slide, I tried to use this standard curve with my estimates here. So let's pretend we purchased a 3-level calibration kit. Calibration level was 5 millimoles, second one was 3, third one was 1. And so we use a spectrophotometer looking for the turbidity of that, like this. We're going to see how much light passes through. And when we do, at an optical density of 620, we get a reading for calibrator 1 of 2.0. Calibrator 2, the optical density is 1. Calibrator 3, the optical density is 0.05. So what do? Here's my concentration of solution. I know this because the manufacturer told me how much it was. And these were the optical density readings I got on my machine, my analyzer. So if I start out at 5 millimoles and I have an optical density of 2.0, I draw up 5, and where it matches with 2.0, I draw 2.0 and I match it over to where it would reach the 5, and where those 2 lines intersect, I put a dot. I'm going to do the same thing for the 3 millimole level 2 calibrator. What did I get for a reading? 1.0. I'm going to apologize if my thing is not perfect here, but I would draw a line straight up from 3 and a line straight over from 1, and where they intersect, I'm going to put a dot. And then I'm going to get my third one. This is at 1 millimole and a reading of 0.5. So I go to 1 millimole, I draw up, I go to the 0.5 and I draw over, and where they meet, I have a point. Now I have 3 points, but this one had 5, so we're going to ignore those. We then plot the concentration. So we plotted the concentration against our reading. That was that, drawing the 2 lines like that and putting the dot where they meet. And then I draw what's called the best fit line. I'm going to draw a line starting here, and I'm going to use a ruler, and I'm going to find out where the best fit is, where there's almost, for as many points as there are above, there are below. And so this one happened to have had 5 points, so it makes it really easy to draw a best fit. But I would be looking at, if I did this and this, these 2 are right in line, and I would have 1 just slightly below. That's perfect. That's fine. If I draw that down, the great news is it actually goes right through the X and Y axis, so a concentration of 0 would presumably have no readings at an optical density, right? There would be nothing for it to see because there's nothing in it. So good news is our line went right through 0. Now we're going to read our calibrators and controls. And so let's say I'm going to pretend you read the control the exact same way that you read the calibrator or the patient. So we go back and we do this. We run the optical density of this, read through. We get a reading. The difference is 3.2 millimoles. In this case, it happened to be the optical density was the optical density was 1.5. So I want to find out how many millimoles of concentration there was in solution. So I go up to my 1.5. I don't know this, so I can't draw the line up, right? So, but I have this standard curve I created that said when I have an optical density of 1, I have 3 millimoles of solution. So, and when I have an optical density of 2, I have 5. And when I have an optical density of 0.5, I have 1 millimole. So in this case, I know what's the one thing I do know. I did it, and I measured the optical density as 1.5. So I'm going to take 1.5, and I'm going to draw a line straight over my standard curve. And when I hit my standard curve, let's see if I think I'm a little off, but my standard curve, sorry, wasn't quite this big when I did it on the screen. And then I hit the curve, and what do? Then I draw a line straight down, and I would use a ruler, and I would see where it hit. And that's really closer to 3.5 than the 3.2 that I guessed. So the patient would have a concentration in their solution of, in this example, 3.2 millimoles of whatever it was. We would run a level high, a level low, and level normal control. And we would want it to fall within whatever our range is for the control for each of those controls. The quality control has to fall within the expected range before we report a patient result. This is a really quick primer on standard curves. You'll do this again and again in the program, so I'm giving you a quick look at it today. You'll see it again in chemistry. You'll see it probably in hematology. So you're going to see this a few more times. But I figure the more times you see it, the better off we are. So that was the standard curve that I prepared, and I would use that to measure the reading, this transmission of light. And when I do that, I could read it off a standard curve and determine what the concentration of antibody or antigen, whatever it is I'm looking for, is in the patient's solution, or how cloudy this was and how it relates to how much antibody there is. Does it make sense? I sure hope so. Nephelometry is very, very similar to turbidimetric testing. It's easily automated now. It's really easy to do. And instead of based on the principle of light transmission through a cloudy solution or through a well-mixed solution of presumably some antigen-antibody complexes, instead what we say that when the light hits this, I told you when it hits the particles, what happens to the light? The light, as it hits a particle, gets scattered off to the side. Only the light that doesn't hit passes through for turbidimetric testing. So what nephelometry does is it measures the stuff that's scattered. So instead of measuring what passed straight through, the clear solution, that's essentially what we're looking at when we look at turbidimetric testing, how much light passed through because it never hit a little object in there. Nephelometry looks at how much light we scatter away because it did hit a small particle. They have little collectors. They have light collectors here, usually at 70 to 75 degree angles off of the scatter, and we're going to read that also on a standard curve, just the way we just did for turbidimetric testing. I'm not going to do another standard curve, but you would do the same thing. Plot 3 to 5 points of a standard curve, and then read your results off of that standard curve, provided your quality control came in. So, nephelometry is the amount of scatter when, remember, a light passing through it. When it hits a small particle, the light scatters off to the side, and it could scatter left or right. So nephelometry is great because it can detect either antigen or antibody, but it's usually tested with a known antibody. That's the most common method. And we're looking for antigen in the patient. So usually the antigen is the patient unknown. There are two kinds of nephelometric tests that we look at. One is called an endpoint test, where we just let the antibody-antigen reaction go until there's no more binding. This is simple. If complexes, it's very simple, but it's very time-consuming because you just got to let it go till it finishes. It can take days for this to happen, anywhere from a day to 3 days for this whole reaction for an endpoint test to complete. And the other problem is sometimes the complexes, those lattices get so big because we just let this go, they fall out of solution, and it's really hard to agitate them back into solution for testing. So we end up with falsely decreased results. These complexes get so big, they fall out of solution. When we shake it up and we mix it, we can't get it back into solution. They keep falling out before the testing can complete, with falsely decreased results. Less light scatters because all the stuff is down the bottom of the test tube, right? Kinetic tests, on the other hand, you add the antigen and the antibody, and instead of letting the complex formation go till completion, you set the manufacturer sets a time to stop the test. You have to know a lot about the test to do it. So you have to, the manufacturer tells you what the rate of formation is, how rapidly antibody and antigens are known to form. And then you're going to again calculate concentration of complexes, antigen-antibody complexes, based on those standard curves. This is faster than those complete reactions, but I'm not going to say it's fast. It's usually a little bit less than a day. 19-20 hours is pretty standard for these kinetic tests. So better than 3 days, I suppose, but not much more. So those are the two versions of nephelometric tests that we have seen. The next kind of precipitation test we're going to look at is called passive immunodiffusion techniques. And this is a test where antigen and antibody complexes can be measured, not in fluid like we just saw with precipitation reactions, but they precipitate in a gel. They precipitate in an agar gel, something that's a support medium. Antibodies and antigens diffuse. They're inoculated into the gel, and they migrate towards each other, as two things that are opposites are prone to do. So antigens and antibodies migrate towards each other, and where they meet, they form a precipitate. They form those soluble complexes. They form those insoluble complexes, and they precipitate out where the antigen and antibody meet within the gel. We call this passive because we're not necessarily going to, we let the reaction just take place naturally. We're not going to necessarily add any enhancements to it. No electrical charges, for example. Some of the tests that we use to do this are radial immunodiffusion, Ochterlony double diffusion, and some electrophoresis when we start to apply. That we're actually going to start to apply some charges, but it's classified in as a passive immunodiffusion. There are 4 factors that affect the rate of diffusion, most of which make sense to us. So the size of the particle, we've seen this before, that the size of the particle, slower particles diffuse slower, right? No. Larger particles diffuse slower. We saw that when we looked at the electrophoresis of immunoglobulins. Big particles move slower through chugging through the gel. Temperature can affect it by slowing it or speeding up the rate of diffusion. Sometimes the viscosity and hydration of the gel, as well as really other interactions with the other reactants within the gel, can affects the rate of diffusion as well. A couple of the basic sources of error in these gel-based precipitation reactions. We're going to see in a few minutes how we have to inoculate the gel with the samples. And you can either overfill or underfill the wells that are cut into the gel. You can, especially people when they're first learning how to do it, nick the gel, and if you nick it, as soluble antigen or antibody passes through that area of the gel, they don't move very well because you've disrupted the gel. And really kind of imprecise measurement tools, frequently it's in the reading, and you'll see in a minute when we take a look at some of the readings that we have to actually measure the zones of precipitation, and that imprecise measuring is prone to error. So let's quickly look at radial immunodiffusion. It's a really interesting technique. This has no electrical current, as I said, to speed up the process. So we have an agar solution. We have glass slide that's coated with an agar solution. It's got antibody pre-mixed into the gel, and it's spread on the plate. There are little wells cut into the gel, pre-cut wells into the gel, and either whether the patient or a control, either the patient or the known control antigen is applied into the well. So remember, we have antibody in the gel, and then we apply antigen into the well. And what happens, because this whole slide is covered with gel infused with antibody, the antigen diffuses out till the point of equivalence, where it means what? There's equal amounts of antigen and antibody. And so the antigen can't diffuse anymore. So when the antigen is all used up, it doesn't go any further. So that's called the zone of equivalence for this, or the point of equivalence. I don't want to confuse it with the zone of equivalence. Basically, it's telling us that we've used up all the antigen that we put into that little well when we inoculated it. And it forms a ring because, again, there's no electrical current or anything that's telling it which way to diffuse. So if this whole slide is covered with antibody, if we put the corresponding antigen in here, it is going to bind out in a ring all the way around. The precipitation goes out in all directions from the center. And what we do is we literally measure the diameter of the ring. And we are going to use a calculation where we take the square of the diameter is what's said to be directly proportional to the antigen concentration. So we have the bigger the diffusion, the bigger the diameter squared, the more antigen there was in the well that when we put in, which makes sense. If you have very little movement from the point of, so this was our standard 1, standard 2, standard 3 to make our standard curve. So this was a low level, and if you look, standard 1 had a concentration of 7 milligrams per deciliter. Standard 2 had a concentration of roughly 15 milligrams per deciliter, and standard 3 had a concentration of roughly 25 milligrams per deciliter. And whatever this, the diameter squared of the precipitation ring, this is in millimeters squared, they measured it. So this standard 1 had probably 8 millimeters, standard 2 was probably 16, and standard 3 was 18 or something. But really it makes sense. The larger the precipitant ring, the larger the amount of antigen we first put in. Perfect sense, right? This was a 3-point standard curve. You would measure this, square the diameter, and measure it on to whatever you get. This was the patient right here. So this was, say, 13. Read 13 across, you go to the concentration, and the concentration is 11 milligrams per deciliter. That's really rough. You would do this with something more than a pointer on a computer screen. But this is radial immunodiffusion. Very straightforward, pretty easy to do. Ochterlony diffusion, a little confusing sometimes, but this really is it's called a double diffusion technique because antigen and antibody independently diffuse in two different directions. They pass through the medium both horizontally and vertically through the solution. So the passing goes up and down and side to side. So what do we know about these test setups? We're going to see wells. I should have put a picture on this slide. Wells are cut into it. I'm going to read while you do this. I have a printout of this so you can see. This is what an Ochterlony plate usually looks like. It has usually six outer wells and one inner well. In this case, they just gave you samples of it that were really small for identification. But wells are cut into the gel, and then there's one center well. Into these, we are going to put antibody and antigen of known and patient, known and patient, known and patient, and then this is going to be a cocktail of multiple antibodies there. And lines of precipitation are going to form. It's hard to see on this one. We're going to see a little line of precipitation that formed. That's going to help us identify what kind of antigen there is. Three patterns of line formation can take place in an Ochterlony diffusion test. They're called patterns of identity, non-identity, and partial identity. And so if we look at this slide, we can see that, let's look at A first. We'll look at A, remember this is multiple, it's sort of a multi-specific antibody is placed into the central well. So that would be this well here. And it diffuses out through the gel towards antigens that are placed in here. One of this is going to be, it doesn't matter which it is, but one's going to be a known, so a control, plus, say, a patient here. And so you would do, in this case, in a real one, you do a known and a control, a known and a control, a known and a control. And then based on the patterns that you see developing, whether you get this arc, you get a cross, an X, or you get what's called a spur, where one line reaches towards one of the antigen wells more than the second line does to the other one. So this little area is called a spur. This is going to tell us, and we're going to talk about in a second. This pattern identifies this as serological identity. The antigens from the patient is the same as the one in the control standard that we put in there. When we get this X in the middle, this means that the antigen of the patient is not the same as what we put in for the control. So if we know that we put in, I'll do something really simple. We put in an antigen. We put in an E. coli as our standard in here, and we put in the patient sample, and we didn't know what it was. We had antibody to a epitope on E. coli. When we get this line like this, we know that this antigen is not E. coli. It's not the same as this. When we get this pattern, same thing if this was E. coli and this was unknown, we would know that this was this was the same. These were the same. And when we get this kind of a reaction, we know that this is similar. Maybe it's a different, slightly different. It's slightly different. It has many of the same characteristics of the epitope, but it's not going to be identical. That's what we call partial identity. We partially identify what this is, but it doesn't really tell us for sure. So let's look at, I got a little ahead of myself. Let's see, did I want to say anything about this? Multi-specific antibodies diffuse out. So the arc of precipitation, I think I said, is that both the known and the patient are the same. So whatever we put in here for the known antigen we have the same patient antigen. So we can identify what this patient has for an antigen. This X is non-identity. So I always remember, that's how I always remember it, is like X is a no. No, this is not right. The known is not the same as the patient, so they'd have non-identity. We didn't really get an answer for the patient other than we know what it's not. And again, when we get one line of the reaction spurring towards one of the antigens, it indicates that one of the antigens has partial identity. So if we had, they have some epitopes in common. Remember, the same epitope can be found on multiple things. It just isn't necessarily the same antigen. The thing to remember about this spur is this spur always points towards the antigen that has the fewest number of epitopes. It's one of the characteristics of the way that the gel moves, the antibody moves through the gel. That when it creates this line, in this case, the known, if this was our known and this was our patient, the known has fewer epitopes of whatever the antigen is compared to this. It's partial identity. So there's other things here that are not going to react. This test is used most commonly for fungal antigens. And it's frequently it's not always easy to grow funguses, and nor are they very quick to grow. So you can sometimes identify fungal antigens like Aspergillus, Blastomyces, Coccidioides, and Candida. So you would put, you could put a Candida here, the patient. Then you could put, another kind of form of a yeast, and then another patient have hiccups. So you can use it like that. And this pattern, remember, what does this pattern mean? This arc is referring to what? The patient has identity. Means the patient and the patient and the known are the same when you get that arc, right? That pattern suggests identity. An arc pattern suggests identity. An X pattern suggests what? Non-identity. And a spur suggests what? Partial identity. So question number 2 on Ochterlony patterns for your homework. What does this pattern suggest regarding antigenic identity? It suggests identity. The patient and the unknown the unknown and the known are the same. Let's move on to electrophoretic patterns. Electrophoresis is really, we've talked about it briefly already, is an immunodiffusion technique that we combine with electrical current. And what does that do? Speeds things up a little. We separate the molecules in gel via by applying an electrical current. We know that small molecules move faster than big ones, and that for immunoelectrophoresis, antigen and antibody will migrate through the gel faster because we're applying that electrical charge. We can either do single diffusion, in one direction, or we can do it in 2 directions, vertically and horizontally. So let's take a look. 3 techniques we're going to sort of look at: rocket electrophoresis, immunoelectrophoresis, and immunofixation electrophoresis. Immunofixation electrophoresis is really what we focus on now. I didn't want you to not know what rocket electrophoresis is. I'm worried it's going to be on the ASCP exam. I don't think they've taken it off yet. So rocket electrophoresis really just talks about when you have an antigen. So this is gel, and this has antibody in the gel. So it's all over the plate. It's got antibody in it. And you put antigen into the wells, and this is in increase in concentration. So you are the things that when we look at this, the further that the tip of the rocket is from the point of inoculation, the further that it travels, it just means that it's an increase in concentration. So one where the tip of the rocket is very close to the antigen well, that's a low concentration. One that traveled further is a high one. That's all it means, and it's moving towards a positive charge. That's about as much as I want you to know about rocket electrophoresis. Immunoelectrophoresis is a two-dimensional electrophoretic diffusion technique, and how this works is that antigens get separated based on kind of their electrophoretic mobility. So we're going to electrophorese the antigen, and what we do is instead of adding the antiserum to the agar, we add it to a trough. And so first, what are we going to do? We're going to inoculate the gel with sample, and then we're going to add antiserum to the trough, and they move towards each other, and where they meet, you get these little lines of precipitation. This is, that's the first step. So that's the first step. So once we've done that, we're going to secondarily take the sample, and we're going to run it at, we're going to take these once they're separated, and here's the antigens that we had put into the wells right here, and we're going to have a little trough with antibodies. So I apologize. First, we're going to electrophorese the antigen through here, and then we're going to add antibody to the trough, and we're going to see how well they get across to each other. And that's where you see the lines of precipitation. And so you develop these strange lines of precipitation like this. The area underneath the peak is reflecting the concentration. So this isn't a great picture because they're all the same. But the greater the difference, the line, the difference in the from the point of origin to the point where it meets the antibody, and diffusing of the antigen towards it, it means there's more antigen. Why is that? Because it traveled further, right? So that's all we're really looking at, is how far the antigen travels towards the trough containing the antibody. So I apologize if that's confusing. I always do that. That first you electrophorese the antigen, and then you secondarily add antibody to a trough and watch the precipitation form. So the precipitation doesn't form right away. Okay, this is where we're going to spend a few minutes. Precipitation, immunofixation electrophoresis. Most of the other electrophoretic techniques really have been replaced by immunofixation. And very much like the immunoelectrophoresis we just saw, first we put an unknown antigen that gets phoresed through a gel, and after, antibody actually is going to get applied all across the gel. Do I have a picture of this? I don't, not of the setup. I don't think that it's in the book. There is not. So it's okay. It's more the principle of the test that I'm interested in. So, so instead of applying the antibody to a well, we're going to apply it to the entire gel. And I'm going to show you I do have the end result in just a second. And by applying the antibody to the entire gel instead of a trough, the diffusion actually goes much faster. It's not doesn't need to diffuse across the entire plate, but it really is just vertically, like up and down. So it takes only like an hour to do this within the lab. So let's take a look at this one. So as I said, immunofixation electrophoresis is a double diffusion technique. First, we're going to apply to a well, we're going to apply This one doesn't have a positive and negative charge. We're going to apply the antigen to a well. It's probably going to be up here. So there'd be a well, a well, a well, a well, a well, and a well. And so we first do that, and then we let it go through the solution, and we're going to apply electrophoresis, and we're going to have it separate out. Then we go back and we apply a gel solution all across the whole electrophoretic plate. And now the antibody and antigen reaction only has to go up a very small amount vertically because we've already electrophoresed the antigen across the plate, right? And we're going to look for where the I can't even go back and say this. The antibody, if we look at, there's actually kind of 6 individual wells within here. So we're going to put antibody here, antibody here, antibody here, antibody here, antibody here, antibody here. And they're going to be different ones. So we actually have like 6 little individual gels here. Talking ahead of myself. So we have added 5 known antibodies. So what's this? This is a lambda. It's a light chain, right? A kappa light chain. An IgM, a mu heavy chain, an IgA, an IgG, and then we have what's called an SP, which is the reference lane. This is all the serum protein. So we're going to overlay a really diverse antisera that contains all the serum proteins that we need. And where the precipitates form here, this one has first when we applied it to the well, we migrated the antigen, and then we migrated it to meet the antibody that we placed on top of it. And where they meet in kind of a horizontal and vertical double diffused technique, where that combination takes place, that tells us what kind of antigen antibody reaction has taken place. So in this technique that we see here, what we see is this again is all the serum proteins. So we see all the different proteins that are contained in serum, in a reference serum. But this patient has an IgG with a lambda chain, so that the immunoglobulin that we're looking at in the patient's serum to see what's in concentration happens to be an IgG with lambda chains. You can see a little something happening here, but it's not significant, and it's not what we're looking at. If we had seen, if we had the IgA here and we saw a really heavy chain here instead, we could say that he or she had an IgA with a lambda chain. So you're going to look and see what lines up with what. If it lined up here and here, then we know it was a mu chain. So we would line it up. We're going to line it up against the reference, and when we see that, we see something line up against a reference, we know that that's the immunoglobulin heavy chain, and that's the immunoglobulin light chain that we're looking at. Why do we do this? We're really looking to determine sort of high and low levels of immunoglobulin production. Hypogammaglobulinemias or hypoimmunoglobulins, so low levels, have these kind of faint patterns, and hyper or high amounts of an immunoglobulin represented by these bold and dark patterns here. So question 3 for the homework. In the immunofixation electrophoretic pattern shown below, I shouldn't say below, shown here, what does SP stand for, and what immunoglobulin type does the patient have in this test? SP refers to what? All serum proteins, and we call that the reference lane. So it's the serum proteins, we call it the reference lane. And what kind of immunoglobulin did we say that the patient had? The patient had an IgG with a lambda light chain, an IgG lambda. Yes? All right. And we're moving on to agglutination, and we're almost done. Agglutination is a little bit easier, I think, to imagine than precipitation. The techniques are very, very much the same. And this is a much more visible reaction, so I think it's a lot easier to see. So we just spent some time learning how precipitation reactions involve, soluble antigens and soluble antibodies. Agglutination, on the other hand, is the visible reaction that's formed by insoluble antigens with an antibody, right? So we know that, and it results also in a visible agglutination. So by definition, it's the clumping together of antigen-bearing cells, microorganisms, or particles in the presence of a specific antibody. So we have an epitope on an antigen with its specific antibody. What happens? They agglutinate out, they form clumps, and it's called agglutination. When we are talking about these antibodies, these specific antibodies that react with these insoluble antigens, these antibodies have a specific name for them. They're really still just antibodies, but we call them agglutinins. 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 And let's see, what else do we see here? Particles. So when we said that we have those insoluble particles, those insoluble antigens, there are a number of different things they can be. They can be red blood cells. And when we use red blood cells as the source of the antigen, we call that hemagglutination reactions. Heme, right, for red blood cells, and agglutination. So when the insoluble antigen source is red cells, we call it a hemagglutination. When it's a bacteria, we call it coagglutination. But we can also see particles that can be some kind of an inert particle. It could be charcoal, it could be latex, that we've actually coated with an antigen or, frankly, an antibody. And so those are going to be the sources of that. They don't have a special name. They're just called agglutination. But when if you hear someone talk about coagglutination, they're really talking about having bacteria as the source of antigen. And these agglutination tests, there's more than this. We can classify it as direct, a passive, a reverse passive, as well as a couple other agglutination reactions. We're going to talk about agglutination inhibitors as well, but they're not. These are the classifications that I want to talk about. Let's look just a little bit more closely at the agglutination reactions. And so, as I said, this is agglutination reactions utilize soluble antibody binding to a visible particle, a red blood cell, a bacteria, an inert particle, right? In order for the antigen to bind with the specific antibody. We're really using the same two-step process that we did in precipitation. We're looking at sensitization, where antibody binds to an antigen. Bam, sensitized. That's that initial binding. Antigen and antibody bind at the antigen determinant sites. We know that, right? The second step that we talked about is lattice formation. It's the formation of large aggregates. These are going to be quite large because they're bound to a large insoluble complex or a large insoluble antigen. So these actually form large aggregates rather than just visible complexes. And we know now how lattice formation happens. So I'm not gonna spend time doing that, but we're gonna remind ourselves that lattice formations are stable and they don't break apart very easily. And as I said, antibodies that are involved in the reaction with these large antigens on particles like red cells or bacteria are called agglutinins. But in reality, it's just a fancy word for an antibody. Let's see. The only thing I want to say here is, yeah, no, I think I'm good. Oh, I didn't pass. I went backwards. There we go. Some of the advantages of agglutination reactions over precipitation reactions, or another type of reaction, is agglutination reactions are really easy to do. We see them on a slide with a latex agglutination or in a test tube for red cell agglutination. Really simple, because the complexes formed are very large and visible to the naked eye. No complicated equipment. You can perform them kind of on an as-needed basis, and they're frequently available in some really prepackaged test kits that come with the quality control material right there. I don't know that it's a bad thing, but agglutination reactions are really qualitative. Either it's yes or no. The antigen is present or it's absent. It's a yes or it's no. Sometimes you can do a little tighter on them. You can make some serial dilutions to give a semi-quantitative kind of a result. High, low, 1 plus, 2 plus, 3 plus. But it's not quantitative by any stretch of the meaning. And we already went over the classifications that we're going to go by. Earlier we spoke about the fact that IgMs are really efficient in agglutination reactions, and in precipitation reactions, of course. But sometimes IgG antibodies need to be used, and that's the way the test kit is made. IgG needs extra enhancement sometimes to make the reactions work in the test method, and it has a lot to do with the fact that, unlike IgM, which is relatively big, IgG is a small molecule. IgM is it's a pentamer, so it's a large molecule with a pretty good stretch in its hinge region, whereas IgG, small, has a somewhat restricted hinge. There's a somewhat restricted flexibility at the hinge region, and both of these things, can lead to some lack of multivalent binding and agglutination, resulting in agglutination. We don't always have the luxury of not using it. That's the test method. If we have a secondary exposure to an immune response, we know the immunoglobulin is IgG that gets produced. That's what we have to deal with. So what do? We're going to use some enhancements to improve the agglutination, and we're going to talk about the concept of the size of IgM in just a second. Let's look at that on the next slide. But in general, IgMs are big, and they have a lot of that twister action happening at the hinge region that can bind off a number of antigen sites. They have 10 antigen binding sites, so they're good, strong agglutinins, and sometimes the test methods that use them are quite effective. So let's look, though, how we enhance some of this agglutination reactions that we need to. As I said, there can be some obstacles that occur during agglutination reaction. So, for example, in hemagglutination reactions, red blood cells carry a really small negative charge with them that tends to repel them from each other. And they keep them roughly, 25 nanometers apart. It's fine for IgM that has that 35 nanometer size. So those will certainly bridge the difference between, two red blood cells that are kind of repelling each other. But IgG isn't so lucky. It's too small. So what can we do to reduce that electrical charge? make those red cells move closer together so that IgG can bridge an epitope on one red blood cell and the other. We've got to make that difference. We've got to narrow the gap a little. And we can do this a couple of different ways. Let's see. So one can be, we can add some additives to neutralize the charge. Something like adding, in the blood bank, we see that we use a low ionic strength saline. It's called LISS, L-I-S-S. Neutralizes the red cell charge a little. We can do something like increasing viscosity with something called PEG, P-E-G, that sort of reduces the water around the red cells, and it makes the makes the gap narrow. I said the narrow gap. I don't know what I said. The GaroNap makes the gap be narrowed. Sometimes we can use some enzymatic treatment, so we can use a viscosity enhancer like PEG to reduce the gap. We can treat the antigen with some enzymes, also eliminating some of that charge difference. What else can we do? We can do some agitation and centrifugation to really, sort of shake the cells back into a closer arrangement. It really is quite literally a mechanical forcing of the cells back closer together. What else can we do? We can change the pH slightly. It may have an effect of enhancing the reactions. Sometimes we can change the temperature of the reaction. I think I said earlier that IgM prefers sort of 30 to 37 degrees room temperature-ish or below. It's a cold. No, I apologize. IgG is 30 to 37. IgM prefers really cold, 4 to 27, roughly. So IgM prefers room temperature or below, really cold. Remember, IgM is a cold antibody. IgG is a warm antibody, likes a nice 37 body temperature, but it will go down. Still reacts as low as, say, 30 degrees centigrade. So we can adjust the temperature to enhance agglutination. We can, as I said, adjust the pH. This is kind of the optimal pH, and if the pH of the solution is off, we can adjust it. And sometimes we can enhance agglutination by just letting the antigen and antibody sit together a little bit longer and letting that reaction take place. Let's look at some of those agglutination reactions that I spoke of. The first one is called a direct agglutination reaction. And, this is the first of the 3 agglutination reactions that I showed you on the other slide. Remember, it was direct, passive, and reverse. So what do we know about direct agglutination reactions? Well, in this case, the antigen is found naturally on the particle. Red blood cells have red cell antigens on it. We know that, right? Bacteria have antigens on them. They're found naturally on it. These are the reactions. Direct agglutination reactions are the ones where soluble antibody binds to those naturally occurring antigens found on the particle. Remember, in red cells we call it hemagglutination, and in bacteria we call it coagglutination. Some of the tests that we use a direct agglutination test, where we're simply mixing antigen and antibody. Blood grouping, ABO, RH, the antigens on the cell. Sometimes we can run tests where we look for bacterial serotyping, or tests where bacteria are difficult to grow in culture. So we want to see if there's a very specific serotype of a bacteria, or something like diseases that we don't really want to necessarily grow in the lab, or they're kind of fastidious. I don't know if you've used that word in micro yet, but they don't like to grow well. Things like tularemia and rickettsia, typhoid. Those are things that we maybe can't grow a culture, but we can look and see if the patient was exposed to it by looking for antibody in their serum, right? So we can test with a known antigen and test the patient's antibody to see if they've been exposed. And how do we do it? We use known bacterial antigens to just test for the presence of those antibodies in the blood. Direct agglutination is used also in something called the Wedel test, which screens for typhoid. And it's not used in this country a great deal anymore, but in other parts of the world, it's really rapid screening to see if someone has been exposed, and uses antigen from a specific, from Salmonella O, and some H antigens or flagellar antigens, and you screen the patient's serum to see if they have antibodies, and if they do, it's presumptive for typhoid. The one that we think of the most in hemagglutination really is the ABO and RH, and I'm not going to spend a lot of time on this because I know you did it, but this is the tube test method that is one of the methods that gets used. But in this case, so we're looking for in the blood bank and direct agglutination reactions, we have anti-sera. This is an anti-A. How do we know it? It's blue. We have anti-B, and this is a yellowish. And so what we're looking for is to see if a patient has an A antigen on their red blood cells, which would make them a type A blood or an AB. And if they have a B antigen on it, they're either a B or an AB. And O, we know, has no A or B antigens on it. So there's other antigens that we don't talk about here, but that's not what we're testing. So if the patient has type A antigen and we mix it with type A antisera, we get this agglutination. If we mix it with type B antisera, then you really just end up with the red cells sort of falling out of solution, but they're not clumpy like a positive reaction. Similarly, mix a patient with B antigen on their red blood cells, it has to mix with B antisera to be positive. Why do people with type AB blood, red blood cells that have A antigen and B antigen react with both? Because they have both on their red blood cells. So their red cells react with A antisera and B antisera because they have both types on their blood cells. And O has neither A nor B, so there's no reaction. And this was just the grading of the reaction. So it's not clumpy, it's just red cells mixed in solution, and this, once they start to clump out, it's a positive test. And this is, remember, we call it a hemagglutinin test. Co-agglutination is, as I said, uses known bacterial antigens. And I just gave you the example of the Wedel test. And really, one thing they do with these kinds of tests is they may look at the concentration over time. They may look and see, kind of the titer of this over a period of time to see if it increases or decreases as a reference of whether or not they have an active disease or it's ongoing. Question 4 for us. The difference between co-agglutinin and hemagglutination is, that shouldn't be I period, S period. What's the difference? They're referring to what the carrier particle is, right? The carrier particle for co-agglutinin is what? Yes, it's a bacteria. And the carrier particle for hemagglutination reactions are red blood cells. So the answers are, the difference between them is the carrier particles, and co-agglutination is bacterial, and hemagglutination is red blood cells. The next kind of agglutination reaction are passive agglutination reaction. Might be easier if they were called by their other name more often, but they're not. So passive agglutination is sometimes called an indirect agglutination reaction. And in passive agglutination reactions, particles like red blood cells or those inert particles like latex or even some natural things like gelatin or silicates, synthetic beads, any kind of particle, are coated with antigens that aren't normally found on that cell. In other words, a known antigen gets attached to a carrier particle, intentionally attached to a carrier particle, and then we can test using that antigen against the patient's serum to see what the antibody is, and see if the patient has developed antibody because they had prior exposure. As I said, this is just another way to see if patients had either active or prior exposure to an antigen. And some of the ways that we use it is using to detect things like rheumatoid factor, antibodies to group strep A, some of the viruses, rotavirus, CMG, cytomegalovirus, rubella, varicella zoster. And as a screening test, not really great for things like hepatitis and HIV. And one of the reasons that this works so well is that it makes sense that you could attach antigen to an inert particle like a latex bead or a synthetic bead, which, by the way, synthetic beads are preferable because their consistency and size and stability and the number of antigens that can be attached to it. But we can use things like red blood cells too, and viruses are known to spontaneously attach to red blood cells. So that's always a possibility. So we'll continue. So anyway, antigen can get attached to a carrier particle in a passive agglutination. We're going to see an illustration of this in just a minute, comparing this to the next one, which is and again, the antigen is attached to a carrier particle where it's not normally found. Okay, so it's not like looking at a red cell antigen on a red cell, we're attaching something to it. Okay? Reverse passive agglutination is sounds a little more complex, the terminology, than it really is, but simply put, reverse passive agglutination reactions bind antibody to a carrier particle instead of an antigen. So we just saw how antigens get attached to a carrier particle in passive agglutination. Doesn't it make sense that reverse passive agglutination, we attach an antibody to a carrier particle? And what do we use to detect? We use it to detect things like a microbial antigen. So we have a particle, we bind an antibody by a technique we call adsorption, where we coat the particle with antibody, and then we mix it with the patient's serum, and we look for antigens in the patient's sample. Could be something like group strep B, Staph aureus, rotavirus, cryptococcus. We can find soluble antigens in serum, spinal fluid, and urine. And agglutination occurs if the antigen is present in the patient sample. Why? Because we attached the antibody to the carrier particle. So it's a reverse process of passive agglutination. It's very similar in concept. It's just in this case, it's what we're looking for and what's adsorbed onto the carrier particle. Make sense? I think so. So let's compare the two. This picture is also in your textbook. I know it's on page 149. So the first illustration up the top is that of passive agglutination. So in passive agglutination, we start here with carrier particles that we have attached, and this is showing us attaching antigen to these carrier particles. There they are. Now they're all coated, right? We add that to the patient sample. In this case, this has antibody in it. And if they cross-react and they make a lattice formation, if it's agglutination, and what does that tell us? The patient had the antibody to whatever the known antigen was. So we intentionally put an antigen of some sort attached to this carrier particle. As I said, it might have been a virus or something like, group A strep or something. We were looking for something specific, so we attached it to a carrier particle, and then we looked to see if the patient had the antibody. Of course, this comes in a test kit. We don't do it on a case-by-case basis, but this is passive agglutination. And then reverse passive agglutination, what did we do? We attached antibody to the carrier particle. We see it here. Notice that the carrier particle, the antibody has to be facing, the FAB regions have to be facing out. If they are too embedded in the carrier particle and they can't bind to the antigen, you can get false reactions. But anyway, so we're going to bind antibody to the carrier particle. We add that to the patient's serum, which presumably, if it creates a lattice formation, then we know that the patient had the antigen within the sample. So in both of those cases, agglutination means that it's positive for whatever we're looking for in the patient's sample. Simple, right? Not so bad. Agglutination inhibition reaction. Sometimes people get a little hung up on this. I think when we discuss it and then we look at a picture, I think it'll make sense. But you may have to look at this illustration a couple of times. So another kind of agglutination reaction is the agglutination inhibition reaction. In this case, the agglutination inhibition reactions are based on what's called a competition between the particulate and soluble antigens for limited antibody combining sites. What does that mean? What it means is that we are going to add we're going to add some bound antigen and combine it with antibody and also some soluble. And we're going to look for the presence or absence of agglutination. And this is going to be able to tell us used in the detection of certain viruses, measles, mumps, rubella, influenza, parainfluenza, hepatitis B, herpes, syncytial virus. I was going to ask you what a syncytia is, but I'm not going to. And adenovirus. We'll see. I'll ask you in class if I remember it. I don't have a picture of it here, otherwise I would show you. So let's go through the two examples of agglutination reactions, agglutin inhibition reactions, one positive and one negative, and look at the interpretation of them. In the first, on the top, we have antigen present, and we add, this is from the patient. So in both cases, this is the patient sample, this is the patient sample. We're going to show you first the example when the patient actually has the antigen that we have in question. So if we take the patient sample and we add antibody to it for what we're looking for. So let's say we're looking for, again, we're looking for, measles or mumps or something. See if the patient has that antigen. We add let's say it's measles, we add or mumps, whatever. I don't even care. We're adding an anti-measles antibody here and against the antigen. And if the antibody and the antigen are the same, the antibody has binds to its specific antigen, then you notice that we have all of the antibody binding sites bound off by this antigen in the patient's serum, right? So we've bound off all of those. We saw this before when we talked about other reactions, how you can bind up all the antigen binding sites. Then what do we do? But remember, this is a sensitized reaction. Is this visible in the lab to us? No, it's not. So we're not seeing anything yet, right? We're just seeing, all we know is we don't know yet, but there is a bunch of sensitized antibodies in there. What do? We add antigen-coded particles. Remember, we attached an antigen to, say, a latex bead or some other particle. And we add that to this test tube as well. So now I have the patient's antigen, I have the antibody to that, and now I have the latex-coated beads with the same antigen that the patient has that we're looking for. I end up with no agglutination. There's no lattice formation. Why not? Because all of the antigen FAB sites, all of the antibody FAB sites were bound off by the patient's antigen before we ever added for this. So there was a competition for who was going to bind to the FAB sites. Was it going to be patient antigen or reagent antigen coated onto particles? You notice is there any agglutination in here? Any lattice formation? No. So if there's no agglutination, this test is positive for the antigen in question. And we can see it here. Positive for antigen, no agglutination. Why? Because there was a competition for these limited binding sites, and they were all bound off by the patient's antigen before we ever added that secondary antigen. Let's look at an example where there's no antigen. So in this case, the patient sample has no antigen. It doesn't have any of the pathogenic material there, the foreign material. But we're still adding that same reagent antibody that we're looking for. Let's say it's, against mumps or something. We're looking to see if the patient had exposure or has the antigen, still has the antigen. The patient doesn't. So what happens? We bind it in. We have the patient's serum or urine, whatever, add antibody. Is there any sensitization here? No, there's not, because the patient didn't have any of the antigen, right? So all those FAB sites are still open and available. We add those antigen-coded particles that we're looking for, and in this case, they bind to the FAB sites, and they will form. They're not in excess, and they're not competing with something else, so they're able to form those lattice formations. They fall out of solution, and so if you have agglutination, remember these were soluble antibodies. This was a sensitized reaction, right? This makes it lattice formation or secondary formation once we have it attached to this. So we bind it here, we form a lattice, falls out of solution. So if yes, there's agglutination, then the test is negative for the original antigen in question. Patient does not have the disease. Does this make sense? Take a look at it a couple of times if you need to follow it along. Hemagglutination reactions are similar to hemagglutination inhibition reactions are similar to the inhibition reactions we just saw, but in this case, we're looking for antibody in the patient sample. And as I mentioned before, some certain viruses can spontaneously agglutinate to red blood cells. In the presence of, in the presence of certain viruses, red blood cells can spontaneously agglutinate, not bind to. This is the principle of hemagglutination inhibition tests. We have a patient sample with antibody in it and one patient with no antibody. So this is the patient sample again. We add a viral antigen in both cases. In this case, because the patient had the antibody, we bound off all the antigen binding sites to the antibody, and then we add red blood cells. And because the viruses are all bound off to the antigen, to the antibody, the viruses are all bound off to its specific antibody. There can't be any lattice formation with the antibody. nor is there any binding between antigen and red blood cells. So in this case, no agglutination means the patient has the antibody. And it's not agglutinating because the viruses have bound off all of the FAB sites for it. So that's the first one. In the second test, in a negative test where there's no antibody, patient has no antibody, we add the viral antigen that matches to it. So we're looking for some form of a virus, right? We add the viral antigen that would normally bind off to the antibody if it was present. Did any immune complexes form? No, because there's no antibody there, right? Patient didn't have any antibody. We add red blood cells, and they can agglutinate. They form a complex and fall out of solution, and we get agglutination. Not because the red blood cells were bound by antibody, but instead because they're bound by viruses. They agglutinate with viruses. Falls out of solution. So if we have an agglutination, a hemagglutination in a hemagglutination inhibition reaction, agglutination means it's a negative test. So look at these examples again, follow through on them, walk yourself through them a couple of times. It will make sense. I have a little table at the end that can walk you through this as well. But remember what you're looking for in a hemagglutination inhibition test. We're looking for the presence of antibody. We had reagent virus. And then the difference is, did the virus bind off the FAB sites, or did the virus remain free? And when we add red blood cells, if there's free virus, it can bind to the red cells and make them agglutinate. If the virus is all bound off to antibody, no agglutination occurs, either by lattice formation with the red blood cells, but these are not what this antibody is looking for anyway. But there's no binding to the red blood cells because virtually all of the virus is bound off to the antibody. Here's comparisons of the agglutination reactions. You can follow along with those. Then quality control, our last slide. Yay, thank you for your patience, people. Quality control and quality assurance. Couple of things just to remember. Make sure that we can remember that antibodies can cross-react with other antigens, right? Not just the one it's specific for. How do we get around this when we're using tests like this? Those antibodies that like this, the reagent antibodies that we provide. How do we get around having cross-reactivity? By using lab-created antibodies called monoclonal antibodies. We develop a antibody to exactly the antigen we want, and then we reproduce it in the lab. So it's a man-made reproduction. It's a clone of the antibody we want. So it's very, very specific to a unique epitope. Always make sure the immune reagents are highly sensitive to temperature and improper storage, so make sure you store the reagents properly. Make sure you get a sensitivity and specificity test kit that's going to be sufficient for what we're looking for. And remember, a negative result doesn't always rule out the presence of disease or antigen. Sometimes we have cross-reactivity, sometimes we have things that don't react. So a negative result does not always prove the rule that there may be a lack of disease. We also saw an example where there might have been an excess of antigen or antibody, for example, that can appear to be negative. We saw many false negative tests as we went through today. So remember, negative test results do not always rule out the presence or absence of either the disease or the antigen. And so that brings us to our last question. True or false? A negative agglutination result effectively rules out the presence of disease or antigen. And as we just know, the answer is no. It's not always, it doesn't always mean negative. So you can go through the summary yourself, but for now I'm going to say goodbye. Read the text, read the PowerPoints again, and ask questions if you have any. You really just have to spend some time with this. Go through this, and then if you have any questions, let me know. And I think that's it. I will talk to you soon. Thanks. Bye.